and it'll record your hand and whatever movement in there. Okay, this is a question that has to do with divider circuits, and it is very similar to the circuit that we just looked at for resistance reduction. But I'm going to show you from that circuit how you can use both voltage and current dividers to determine circuit element values. So the first thing we're going to look at this is part number A. We're going to determine the power consumed by the 40 volt source. So we're looking at this 40 volt source. We want to determine the power consumed there. And the second thing we want to determine is the current in the 5 ohm resistor and the voltage across the 20 ohm resistor. Alright, so we've got a couple of things that we need to know from this circuit, and we want to be able to work through this circuit. So first I'm going to start off. I recognize that this has one source and all the rest of the circuit elements are resistors, and so I think there's a possibility of using resistance reduction. When I look at this resistance reduction, I look at this short circuit on this side and recognize that this 80 ohm resistor and this 20 ohm resistor are in parallel with each other. And so there's a combination that I can produce there, and so that 80 ohms multiplied by 20 ohms divided by 80 ohms plus 20 ohms works out to be 16 ohms. And so there's an equivalent resistance of 16 ohms that will replace that 80 and 20 combination. I've done that for you by doing this, and when we see that combination, we recognize that there's a series element, and these two are in series, and resistors add in series, therefore it's 16 ohms plus 4 ohms, which is a total of 20 ohms. And so they replace that combination with 20 ohms, and I'll do that for you very quickly. And we then see that there is a parallel combination of these two, and we find that we have 20 ohms times 5 ohms divided by 20 ohms plus 5 ohms, and this is equal to a combination of 4 ohms. So we can replace the entire resistive network with a 4 ohm resistor. When we replace it with a 4 ohm resistor, we find that there are 40 volts applied across 4 ohms, which gives us 10 amps. Alright, so now that we've solved the circuit in its simplest form, we now have to go back to the original circuit and find out what the various currents and voltages in all of the other elements are. So we put that back. Alright, we saw that 20 ohms is in parallel with the 5 ohms. We saw that there was a current of 10 amps there, and that 10 amp current now divides between the 20 ohm resistor and the 5 ohm resistor. And so the current in the 5 ohm resistor is the 5 ohm resistor is the smaller of the two resistors, therefore it's going to be the largest of the currents. So we take the 20 ohms divided by the sum, which is 20 plus 5, and we multiply that by our source current, which is 10 amps, and we have 20 divided by 25 times 10, which is 8 amps. And so there is 8 of those 10 amps going through the 5 ohm resistor. Well, we immediately know that the other one has 2 in it, but let's just work it out. The current in the 20 ohm resistor, since the 20 ohm resistor is the bigger of the two resistors, the smallest amount of current will go through that branch, and so therefore we use the smallest number, which is 5 ohms, divided by 20 plus 5, there's our current divider, all multiplied by 10 amps, which is equal to 2 amps. As we expected, there will be 2 amps in that branch. Well, we can take that branch back to its original form by taking the 20 ohm resistor and dividing it back into its 4 and 16. We knew that there were 8 amps in this branch. We know that there are 2 amps in this branch, and so we could use that 2 amps to determine what the voltage across the 16 ohm resistor, but we also can use a voltage divider. And so if we use a voltage divider, we'll find the voltage across the 16 ohm resistor is equal to, notice that this is all one short circuit down through here, and so therefore the 40 volts is applied across that series combination, and the current here is 0. There's no current at that central node, and so therefore this is a complete voltage divider, and so therefore the voltage across the 16 ohm resistor is 16 ohms, which is the voltage across this, right, divided by 16 plus 4, all multiplied by 40. And so therefore this is equal to 32 volts. 32 volts from our voltage divider. We could have determined that because it was 2 amps multiplied by 16 ohms. It should come up to 32 volts. And so either way, you can use the current, or you can use the concept of a voltage divider to determine what the voltage across the 16 ohm resistor is. But we recognize that that 16 ohm resistor is a combination, and that combination is made up of a 20 ohm resistor and an 8 ohm resistor. And so that we can determine that the voltage across that 20 ohm resistor is 32 volts. Just the same as the voltage across the 80 ohm resistor is also 32 volts. And so this parallel combination has the same voltage across both elements, and that voltage is 32 volts. So now we've taken a circuit that has a source and several resistors. We have done resistance reduction to determine what the current from the source was. We saw that the current from the source was 10 amps, and so therefore the power in the 40 volt supply is equal to voltage times current, with the exception here that the current is leaving the positive terminal. When the current leaves the positive terminal, we have to put a minus sign out there. And so therefore this becomes minus 10 amps times 40 volts, which is minus 400 watts. So this is the power consumed. The power consumed is minus 400 watts, and so therefore it is 400 watts delivered. Right, so that's the power that's dissipated in that 40 ohm supply is a minus 400 watts, or the power supplied by that 40 volt supply is 400 watts. All right, thanks for watching. See you.